Hello, everyone. Welcome to the Origin seminar this week. This week, we have a speaker, Akash Gupta. He is a PhD candidate at UCLA. He's about to graduate next year, so he's on the job market right now. So please looking for his application and see if I have some positions. So he's working with Professor Hugh Schlichting,
Yeah.
and he has a very broad interest in all topics related to the exoplanets. So he also has collaborated with Professor Lars Dijkstra and several other professors. Okay, floor is yours.
Thank you so much. And so just to confirm, can you hear me all right?
Yes, we can hear you.
Okay, sounds great. Hi, everyone. First of all, thank you so much for giving me this chance to share my work with all of you. And yeah, so in this talk, I would like to share with you how we can understand the planet formation and evolution process from the galactic to the atomic scale.
Oh, actually, we couldn't hear you for a bit.
Oh, okay. Sorry, let me just change things a bit.
Now it's okay.
Okay, now it's okay. Okay. But yeah, please do let me know if at any point, there's any problem with hearing what I'm trying to say here. So, okay. So to get started, so I'll try to describe as we go through, what really I mean by this. Now, this is based on the work I've been doing with my PhD advisor, Hilke Schlichting and Lars Dijkstra. In addition, as we go on, I will also highlight the work that my undergraduate mentee, Lauren Nicholson, has contributed to, and my collaborations with James Owen and James Rogers. So, to get started with, in our galactic neighborhood, way back in 2000 BC, we already knew of these 6 planets. And things did not really change in the next 4,000 years, where we only got to know of 2 new planets out there. And this really puts into perspective the magnitude of the discoveries we have witnessed in the last quarter century, where we have come to discover more than 5,000 planets in our galactic neighborhood. And these discoveries have really challenged our understanding of how planets form and evolve over time, and have surprised us with so many new mysteries. And one of the most profound findings from this time is actually this lack of planets around 1.5 to 2 Earth radii. So what you are seeing here is that in this y-axis, the number of planets, on the x-axis, the planet size. And as you can see, there are very few of them around this 1.5 to 2 Earth radii. This has come to be known as the Radius Valley, and basically divides this planet population, specifically the population of the most abundant planets that we know today, in these small super Earths, which are likely rocky and with Earth-like bulk composition or bulk densities, and these sub-Neptunes, planets which are larger, puffy, with low densities, and likely have hydrogen atmospheres, icy interiors. So this is telling us that this Radius Valley is like this transition regime between 2 very different classes of planets, from these rocky super Earths to these gas-rich sub-Neptunes. And this naturally leads us to, makes us ask many questions. Questions like, why does this Radius Valley exist? Do super Earth sub-Neptunes have a common origin? And if so, how did they form? Or do they form through distinct formation and evolution pathways? What are the characteristics of these planets we are observing today? Are the rocky super Earths, in fact, Earth analog, or is there more to them? And how does the stellar environment influence a planet's evolution? And so on. So, to figure this out, let us start with the very first question here. Why does the Radius Valley exist? Now, numerous theories have been proposed to explain these observations, but only a few can explain a multitude of the Radius Valley observations. The leading idea today is that atmospheric mass loss, driven by photoevaporation, or core pod mass loss, can explain these observations. The idea behind photoevaporation is that the high energy radiation from the host star can heat up the upper layers of the atmosphere and can drive atmospheric loss. Whereas core pod mass loss is what much of my PhD thesis has been focused on. So let me walk us through what is the idea behind this, what insights this gives us into the planet formation process, and what predictions we can make for the future. So the story of planet formation starts with this protoplanetary gas, with this gas cloud collapsing under its own gravity, leading to the formation of a star and an optically thick gas disk around it. In this gas disk, as things cool down, particles start to form, collide with each other, and you basically get the process of core accretion. Now, during this process, as things are coming together and colliding with each other, all that gravitational binding energy is basically converted into heat energy. Now, all this heat energy can get radiated away very quickly if this process was happening in empty space. But this process is not going to be as efficient if there is an optically thick gas disk around you. More importantly, once the boundary radius of the planet, by which I mean the distance from the planet where the gas molecules have enough energy to escape the gravity of the planet, once this boundary radius of the planet becomes larger than the physical size of the planet will start to accrete an atmosphere, a hydrogen helium atmosphere in this case. And to zeroth order, this tells you that there can be a lot of energy in these planets at this point. And so as the planet starts to accrete an atmosphere, it will grow with time. And very soon, this envelope will become optically thick. And once this envelope becomes optically thick, any energy loss from the planet will basically be regulated by the radiative diffusion across the radiative convective boundary. And what that will do is that will increase substantially the cooling timescales of the planet, or basically that will slow down the process of the planet losing its energy, primordial energy. And so basically you will have this baby planet which can stay warm and cozy for a much longer time than what you would otherwise expect. Now, before I move on, let me just describe what kind of planet am I imagining here. So what is the planet structure of our model planets? And this is how things look like. So we have a planet which has a core. This is the astrophysicist's core, basically everything except the atmosphere, surrounded by an atmosphere which has an inner convective region and an outer radiative region. In the inner convective region, I assume that we can very well describe it using an adiabatic profile. In the radiative region, we assume that the atmosphere is isothermal. And so because the atmosphere is isothermal here, what that means is that the density decreases exponentially with distance. And that implies that much of the atmosphere's mass is in fact contained within the convective region. That also more or less implies that the visible radius of the planet is roughly this radiative convective boundary. So keeping this in mind, at a later point in the planet's evolution, the idea here is that the planet can end up experiencing a Parker-type hydrodynamic outflow because of the internal energy of the planet and the host star's bolometric luminosity, causing atmospheric mass loss. So if a planet evolves in this manner, it can either end up losing all of its atmosphere, and in that case, it will end up becoming a super Earth. If it is able to hold on to some of its atmosphere, it will become a sub-Neptune. But then we should be asking that, what is it that dictates if a planet becomes a super Earth or a sub-Neptune? A number of things matter for this, but the key is this balance between the cooling and the mass loss timescale. What is the idea behind this? Well, for that, consider this case where a planet predominantly cools with time. For such a planet, as it is cooling with time, it is losing its energy and its atmosphere is shrinking with time. And so over time, the atmosphere is going deeper and deeper in the gravitational well of the planet. As that happens, it will become harder and harder for the planet to lose any bit of its atmosphere, because you will have to inject more energy into any atmospheric parcel for the planet to lose it. And what that implies is that very soon the planet will stop losing any atmosphere and will basically become a sub-Neptune. The exact opposite will happen if the mass loss is what dominates. The planet will end up getting into a runaway process and will become a super Earth. And so this explains this bimodality in the final planet outcomes of a super Earth and a sub-Neptune, gas-rich sub-Neptune. This, along with the fact that the atmosphere size the planet size can almost double if the planet has even a little bit of, like a few percent of hydrogen helium atmosphere by mass. That explains this radius valley and this sudden jump in planet sizes from these rocky super Earths to these gas-rich sub-Neptunes, which are almost double the size. So what we do is that we use a simple analytical description for a planet's thermal evolution and atmospheric mass loss and try to understand the impact of this mechanism on the demographics of Earth to Neptune sized planets. While assuming that all planets formed when the protoplanetary disk was still around, and so they formed with primordial hydrogen atmospheres. So let us see how our results compare with observations, what insights they give us, and what predictions we can make for the future. First of all, let us focus on the planets around sun-like stars. And so what you're seeing here is, as before, this plot is showing how the relative occurrence of planets changes with planet size. The red curve here corresponds to our model. The gray curve corresponds to observations. The two right-hand side plot show the very same thing, but in a two-dimensional space of planet size and orbital period. The color here corresponds to the relative occurrence of planets. Now the middle plot is our model. The right-hand side plot are observations. Now just to remind you again, this is basically the same plot as before. And now this is the super Earth population, whereas this is the sub-Neptune population, and this is where the radius valley lies. And as you can see, there is a good agreement between our results and the observations in the sense that where exactly the valley is located, the relative occurrence of super Earth and sub-Neptunes, and the general shape or slope of the valley. But then at this point, we should be asking ourselves, why is this agreement there? Like, what insight is this mechanism giving us into the planets we are observing today? So to answer that, let us try to understand one of the most characterizing features of the radius valley, its slope, something that has been noted across like phase space of different planet and host star properties. So the idea here is that, as I was mentioning before, the sub-Neptunes are the planets which predominantly cool with time. That is, for these planets, the cooling timescale is shorter than the mass loss timescale. Whereas for the super Earths, it is the mass loss that dominates. That is, the mass loss timescale is shorter than the cooling timescale for these. This is telling you that it is this balance of these two timescales that dictates where a planet ends up. And so we should be able to figure out the slope of the valley by just comparing these two timescales. Things become even more simpler when we realize that the mass loss timescale has an exponential dependence on certain parameters, whereas the cooling timescale does not. What that means is that how this equality depends on different parameters really boils down to the expression in the exponential for mass loss timescale, which on its part is basically this, which is planet size cube times equilibrium temperature inverse times rho c star power 4 by 3, where rho c star basically represents the composition of a planet's core. In a nutshell, this expression is telling us that the planets that are hotter and less massive are more vulnerable to complete atmospheric loss. Now, because we are interested in the slope in the planet size orbital period space, what we can do is that we can substitute orbital period in place of equilibrium temperature, and that gives us a slope of minus 0.11, which is in excellent agreement with observations. Now, if this is indeed what is happening out there, we should be able to use the very same analytic prescription to explain a number of other observations of the radius valley. And so let us see if that is really the case. So let us have a fresh slide. I basically as I just told you, we can figure out the slope by just comparing these time scales, which basically boils down to this simple expression here. Now, just now we ignored rho c star in what we were talking about. But if you think about it, this is also telling us something about the rho c star also tells us something about the valley. In other words, the location of the valley tells us something about the typical composition of the planets we're observing today. How do we understand this? Take this example of like n-member cases of planets which have like a pure icy core and a planet which has a pure iron core. Now we know that iron core is more heavier, and so the iron core is more denser. And so what that means is that for a certain like given planet size, an iron core planet will be better at holding on to its atmosphere than an icy core planet because it will be more massive. And that is exactly what you're seeing in these plots back here, where I have again the same plots as before, showing the planet size distribution in this planet size orbital period space. On the left hand side for planets which have pure icy cores, on the right hand side planets with pure iron cores. And as you can see, the radius valley is at a lower planet size in the iron core case, exactly because if you are an iron core planet, even when you are smaller, you are just much better at holding on to your atmospheres. And that is why the sub-Neptune population is present at much lower planet sizes. And using this idea, we can predict that the planets that we are observing today should have rocky Earth-like bulk densities or like Earth-like compositions. This is in agreement with direct mass and radius measurements of rocky planets and geochemical studies of polluted white dwarfs. So beyond this point, let us assume that most of the planets we are observing have more or less the same composition. That basically reduces this expression to this. We can then substitute insolation flux in its place. That tells us that the slope in the planet size insolation space is 0.08. In other words, the slope in the planet size insolation space at a constant stellar mass is 0.08. But from a different perspective, this expression also tells us that the slope in the planet-sized stellar mass space at a constant insolation is 0. In other words, for core-powered mass laws, the slope of the radius valley does not depend on stellar mass at a fixed insolation flux. This, however, is not true for photoevaporation, where the high-energy stellar flux, which leads to atmosphere loss under the photoevaporation scenario, the high-energy stellar flux received by a planet changes with stellar mass for a given bolometric flux. And this is exactly what you're seeing in these plots, where we have plotted how in the planet-sized stellar mass space, at a fixed incident flux, how the planet demographics would look like. And so as you can see, for the core-powered mass loss case, we expect a flat slope, indicating no dependence. Whereas in the photoevaporation case, we see a negative slope. And this can be encapsulated in these parameters alpha and beta. And so what this is showing us is that it can be very powerful to explore the radius valley in this three-dimensional space of planet size, stellar mass, and insolation flux to figure out which core-powered mass loss or photoevaporation might be dominating the planet evolution process. And this is something we explored in collaboration with James Rogers and Chip Sowen. In a nutshell, our results look something like this. Now, I'm not planning on going into the nitty-gritties of this, but I'm happy to talk more about it if anyone of you might be interested. But what we basically have here is this beta slope and alpha slope on the x-axis. And we are comparing the predictions of photoevaporation and core-powered mass loss models with the CKS model on the left-hand side, the GKS model, the CKS planet survey on the left-hand side, and the GKS planet survey on the right-hand side. By CKS, I'm referring to the California Kepler survey, where this study used high-resolution spectra to get better constraints on planet radii. Whereas by the GKS, I'm referring to the study by Travis Berger and his collaborators, where they used Gaia parallax to get a better handle on the planet radii. And the main takeaway from this plot is basically that there's a significant overlap from what we expect from the observations and what our models are telling us. So unfortunately, at the moment, given how large these planet surveys are and the uncertainties in the planet radii, it is hard to distinguish which of these two mechanisms might be happening out there. That being said, with surveys of over 5,000 planets and planet radii and uncertainties of around 5%, we should be able to figure out what is happening with this method. Now, getting back here, we can substitute insolation flux in place of stellar luminosity. Sorry, we can substitute stellar luminosity in place of insolation flux, and then using the fact that stellar mass and stellar luminosity are correlated, we can write this in this manner, which brings us back to the expression that we were talking about before. But this tells us another interesting bit this time. That is, in the slope, that the slope in the planet-sized period space is minus 0.11 across the FGKM dwarfs. And this is exactly what you're seeing in these plots. But before I discuss there, I would like to point out that a lot of the results I'll be discussing in the context of M dwarfs are thanks to my undergraduate mentee, Lauren Nicholson, who is now an NSF-GRFP fellow and a PhD student at University of Florida. So what you're basically seeing here now is that planet distribution around a 0.1 solar mass star and a 1 solar mass star. And you can see the slope of the valley is more or less the same. And this, again, is in good agreement with observations of FGK dwarfs and M dwarfs. Getting back to this expression tells us another interesting bit. So now, if you were to assume that across stellar masses, the period distribution more or less stays the same, something that has been noted by CK studies for like up to down to like 0.6 solar masses. So if we assume that, this tells us that the slope in the planet-sized stellar mass space is simply a function of zeta, where zeta is from the mass-luminosity relation, has been observed to be typically more than 2 and to increase with stellar mass between the stellar mass range of 0.1 to 1 solar masses. In other words, this is telling us that in the planet-sized stellar mass space, the slope of the radius valley is positive and becomes shallower towards lower mass stars. You might have already noted this when I was showing you this plot, but should be more apparent here when I'm showing you how the planet size distribution changes in the planet size stellar mass space. A lot is happening here though, so let us break this down and just focus on these 3 stellar mass spin, one around 0.1 solar masses, 0.5 solar masses, and 1 solar mass. So around the 0.1 to 0.15 solar mass case, the missed data sets basically tell us that the zeta should be approximately 2.2, zeta which encapsulates this stellar mass stellar luminosity correlation. And missed data sets are basically these stellar evolution tracks derived from the widely used 1D stellar evolution code, MESA, or modules of experiments in astrophysics. And so this zeta value implies that the slope around 0.1 solar masses should be 0.13. And that is exactly what you're seeing here. Now we repeat the same exercise for 0.5 solar masses and 1 solar mass case. And so as you can clearly see that first of all, the radius valley slope is positive and the slope becomes flatter as you go towards lower mass stars. And this trend is basically encapsulated in how these zeta values change, as I was mentioning before, or as our analytical prescription was telling us. So this is all right. So we have some new predictions, but how does this compare with observations? So on that front, what we did was that we modeled our stellar population after the CKS dataset to figure out how do our results compare with their observations. And this is how our results look like. So on the left-hand side, I'm showing you how the relative occurrence of planets changes in the planet size stellar mass space for our model. On the right-hand side, we have observations from Fodor and Pettigrew 2018. For the CKS dataset, we found that zeta was approximately 4.6 for that exact stellar sample, which gave us an analytic slope of 0.33. And as you can see, we have a very good agreement with observations where both of these, first of all, slopes are similar. And as you can see, the planet demographic, the planet distribution also is in good agreement. And this is not just an agreement with their study, but also a number of other ones that have been published along these lines. So what is happening here in a nutshell is that planets that are more massive and luminous stars which are more massive and more luminous have planets at higher planetary equilibrium temperature. And so even more massive cores are susceptible to complete atmosphere loss around them. And that is why as you go towards a more massive star, the radius valley goes up in planet size. We can use similar ideas to explore a number of other aspects of planet demographics. And I'm happy to talk about any of these if you might be interested. But let me just end with this one last example, where we also explored how the planet distribution changes in this planet-sized stellar age space. So what we basically found that planets lose their atmospheres on gigayear timescales to become super Earths, which is basically what you're seeing in these plots, where the yellow curve shows young planets younger than 1 gigayear, whereas these red and blue curves show planets older than 1 gigayear. This was in sharp contrast to photoevaporation predictions at the time, because most of the atmospheric erosion under the photoevaporation theory is expected within the first 100 million years. That being said, the view has changed since. In any case, this was later observed by Travis Berger and his collaborators in 2020. And that is exactly what you're seeing here. Basically, in this plot, we have number of planets on the y-axis and planet size on the x-axis. The purple histogram shows you the older planets older than 1 gigayear, whereas the green histogram shows you younger planets younger than 1 gigayear. There are two interesting things that are happening here. First of all, the sub-Neptunes are shrinking in size over time. Second is that the super Earth sub-Neptune occurrence is increasing on this gigayear timescale, just as we had predicted back then. So to summarize things to this point, I shared with you about this radius valley, which is this fascinating and unexpected dearth of 1.5 to 2 Earth radii planets that separates these rocky super Earths to these gas-rich sub-Neptunes. And it demonstrated how the score-part mass loss mechanism can consistently explain a multitude of the observations related to the radius valley. The idea behind which is that atmospheric mass loss could be driven by the cooling luminosity of the planet and the bolometric luminosity. Finally, I shared a number of predictions with you, some of which I would like to highlight here. For instance, we find that the typical Earth and Neptune sized exoplanet accretes a primordial hydrogen-helium atmosphere and has an interior of Earth-like bulk density or composition. We find that planets lose their atmospheres to form super Earths on a gigayear timescales. And I also shared a number of planet demographic predictions. For instance, in the planet-sized orbital period space, we expect the slope to be minus 0.11 across the FGKM dwarfs, whereas in the planet-sized stellar mass space, we expect the slope to be positive, but flatter as you go towards M dwarfs. Oops, sorry. And finally, I also shared with you a number of new avenues to explore the differences between the core part mass loss and photoevaporation. For instance, one could be to explore the radius valley in this three-dimensional space of planet-sized stellar mass and insolation flux. And another could be to explore the radius valley around M dwarfs, something I did not talk about. But the thing is that exploring the radius valley around M dwarfs can be very powerful, because as you go towards these lower stellar masses, the predictions of the two theories starts to diverge. So at this point, I would like to highlight one of the things that I just pointed out here. That is the typical Earth-Neptune sized exoplanet. It creates a primordial hydrogen-helium atmosphere. Now, this is unlike Earth, but not that surprising. I mean, in our own solar system, we have Jupiter, Neptune, Uranus, who have hydrogen atmospheres after all. And so this is telling us that the planet formation and evolution process in general entails this interaction of a hydrogen atmosphere or hydrogen with the interior of a planet for millions to billions of years. But planet evolution models often assume that the planet's interior and atmosphere are chemically inert. So is that really a good assumption? So for instance, this is what we were assuming in our study, and many of the photoevaporation studies also assume that. So is that a good assumption? In other words, are these interactions between the planetary building blocks even important for us to care about them? So on this front, I started working with my advisor, Hilke Schlichting, and also with Ed Young here at UCLA to figure out how exactly these interactions happen and what is the implication of that on the planets that we are observing today. And this is something that they recently published about, in fact, and they found that this interaction can be very important to what you're seeing in the atmospheres. It can very much dictate the atmospheric composition, and also things like the mass-radius relations, which are often used to figure out how the planet, to infer what the planets might be made of. There have been studies which have also pointed out implications for the planet demographics, and there are other studies which have talked about how this can have a huge impact on the structure and the thermal evolution of planets. In a nutshell, this is telling us that the interactions between planetary building blocks can have far-reaching consequences and will be important for understanding observations from instruments such as JWST and the Future Uranian Orbiter. In fact, we have observational evidence for this already. Thanks to measurements from Juno, we know that Jupiter's core and atmosphere are not really inert. In fact, the Jupiter's core is diluted because of its interaction with the atmosphere. But the thing is that when you're working on these kind of geochemical like equilibrium models, what you realize very quickly is that we have, in fact, a very poor understanding of how these interactions actually happen. And our best models can only be as good as our fundamental understanding of how these planetary building blocks interact. But then what is the issue? The thing is that these experiments can be very difficult to do. Like, especially playing around with hydrogen is so tricky. So how can we go around this? So to explore that, I've been working over the last year or so with large stakes fluid to understand how we can use quantum mechanics to understand this problem. Specifically, I've been using the method of ab initio molecular dynamics, something that is used across the sciences and engineering, from the discovery of new drugs to discovery of new materials. The idea here is to solve the Schrödinger equation. This is a very involved equation, but in a nutshell, it is simply an energy equation with terms which describe the kinetic energy of the atomic system, terms that describe the potential energy of the atomic system, and some total energy of the system. Now, you might have seen solutions to this equation for like a hydrogen atom. But the thing is that this is computationally intractable for a multi-electron system because of this term. This is the term which basically accounts for the quantum interactions between electrons, and it becomes computationally infeasible to solve this. But a way to get around this is to use the density function theory. In a very crude way, the idea behind this theory is that you describe a many electron system using a charge density which encapsulates the quantum interaction between the electrons. So once you are able to figure out the energy of a system in this manner, you can then figure out what are the forces that are acting on the system, and you can simulate an atomic system to figure out like how, to basically, you can then simulate an atomic system. And to go about it, we basically use the Vienna ab initio simulation package. And specifically, we're trying to understand the formation and evolution of water-rich planets and exoplanets. Specifically because planets like Uranus and Neptune are one of the best laboratories we have for not just understanding our own solar system, but also the evolution, composition, and structure of gas-rich subneptunes. So the traditional view of a Neptune-like planet, let us say, is this, that there's a hydrogen atmosphere, a non-interacting hydrogen atmosphere sitting on top of a water-rich interior. But as I will show you, what's really happening out there is that there are regions which are hydrogen dominant and regions which are water dominant with partial amounts of hydrogen dissolved in it. But then how do we figure this out? What we can do is that we can calculate what is called a critical or coexistence curve to describe this behavior, to quantify this behavior, to figure out what kind of compositional gradients could be present inside a planet and how that could be impacting the thermal evolution of the planet finally. Now, the idea behind the critical curve is this, that in this temperature pressure space, the critical curve is basically what divides this pressure space in regions where hydrogen and water will be completely miscible and where they will not be. The coexistence curve goes a step further and helps you describe, helps quantify what the degree of miscibility of hydrogen and water into each other. And as I was mentioning before, the issue is that we have a lack of experimental data today to figure out what this critical curve looks like for the hydrogen water system. So what I'm showing you here is in this temperature pressure space, what all experimental data that we have. So we have this one data point from way back, like 40 years back, from Seaver and Frank, and then this another data point from Bali et al. 2013. Basically, where the colors are changing is where the critical curve lies. And for context, for Uranus and Neptune, the icy or the water-rich metals can go all the way from 1 to 100 gigapascals. And the x-axis is actually in logarithmic scale. And so that really tells you that we have a very poor understanding of what is happening in these planets. And so to address this, as I mentioned before, what we basically do is that we basically simulate these pure phases of water and pure phases of hydrogen to figure out how exactly they're interacting with each other and try to quantify if they completely dissolve into each other or not. Now, I should mention that the hydrogens there for the water and the hydrogen molecules were color coded differently, but that is only for the purpose of illustration. They can interact like absolutely freely. They can form any species that might be possible under those temperature and pressure conditions. Now, it is not that no study has looked into this system ever. There is, in fact, a study by Sobra and Militzer. I apologize, might be pronouncing their names wrong. But yeah, there is this study by Sobra and Militzer from 2015, and which basically found that in this entire green space, hydrogen and water should be completely miscible. Sorry, just a second. So they basically described that hydrogen and water should be completely miscible in this space. But a number of recent studies have pointed out this discrepancy between what the experiments were telling us and what these results were showing us. And also the importance of quantifying the critical curve and the coexistence curves of the hydrogen water system to really understand what is happening with these kind of planets. So on this front, we decided to go a step further and try to quantify like what's really happening out there. Now, this plot has gotten a lot crowded, so let us cut down things to the main takeaway, that is this critical curve. Now, for context, let us plot the AD bed for Neptune. And so now this plot is basically telling us three interesting things. First of all, this is telling us that in this entire region, the hydrogen atmosphere and the water-rich interior should be completely miscible into each other. Much deeper down, whereas you will expect a compositional gradient as the hydrogen will become increasingly immiscible as you go to higher pressures. And what you will also expect is that as the planet cools, so you can assume that the Neptune's adiabat was roughly this red line way back in the past. And so as the planet cools and becomes from this red line to this blue line, there is a part of the planet's interior where earlier the more thermodynamically stable state would have been for hydrogen and water to be completely mixed, whereas over time it will be more stable for them to be demixed. And this process will contribute an additional energy source towards the thermal evolution of the planet. And so this demixing happening inside the planet can impact the thermal evolution of the planet on like long time scales. Finally, we should always ask that, can this actually be like, corroborated with any like observational evidence? So on that front, what we have here is this plot from Moskowitz and Courtney, which describes the Neptune's interior profile based on observations. So on the y-axis, we have the density. On the x-axis, we have pressure. The dark blue curve here is basically quantifying that to 1 sigma confidence, what can we say about the interior profile of Neptune? The lighter blue curve is quantifying that 2 sigma confidence, what can we say about the interior profile? Now the pressure scales are different in both these plots, but these blue and red panels basically span the same pressure range. So you do not have to worry about reading of these little texts here. But the thing here, the main takeaway here is that, well, first of all, in this entire blue region, you expect hydrogen and water to be completely mixed with each other. Whereas in beginning this 20 gigapascal like point, or like beginning where this red panel starts, you will expect hydrogen to be less and less dissolved, or like as you go further to higher pressures, you will expect purer and purer like water interior. And interestingly, this is exactly where you see this huge bump in the density in the interior of Neptune. And so this is really exciting that what we are finding here, what we are seeing in these observations, like it could be an explanation to what we are basically seeing in these observations. That being said, more analysis is needed. And so this needs to be taken at the moment with a big grain of salt, but something we are working towards. So to summarize things, I told you that how important it is for us to understand this interaction of planetary building blocks, because they can have a big impact on the composition and structure of planets and their atmospheres. But today we have a lack of data that is contributing to our poor understanding. And the thing is that lab experiments are difficult, but we can use quantum mechanical molecular dynamics to get a handle on this better. And specifically, I've been looking at this system of planet's hydrogen atmosphere and water-rich interior. How exactly are they interacting with each other? What we are finding is that in large parts of the planet's interior, these two could be completely like soluble into each other, whereas we expect composition gradient much deeper down. And as the planet cools, we also expect regions of the atmosphere where it will all of a sudden become like thermodynamically more stable to be demixed. And this process will basically contribute to the overall thermal evolution of the planet. Finally, we also find tentative agreement with observations. That being said, more work is needed on that front. So to bring it all to a close, I basically shared with you how we can understand this fascinating aspect of the planet demographics, this radius valley, using the theory of atmosphere mass loss. Specifically, I focused on the theory of core part mass loss, where atmosphere loss can be driven by the bolometric luminosity and the cooling luminosity of the planet. And in this way, how we can explain a number of aspects of planet demographics. And one of the key takeaways from such studies has been that these planets should have a hydrogen atmosphere interacting with the interior of the planet for really long times. And so big question is that how exactly this interaction is happening. But as I mentioned, the thing is that it's really hard to do experiments at the relevant temperatures and pressures. The way to get around that is to use quantum calculations. And specifically, I've been looking at this hydrogen water system, and that shows us that indeed this interaction is important to take into account, because this can have interesting implications for how the planets evolve over time and how they are structured on the inside. And so that is it from me. Thank you so much. And I'll be happy to answer any more questions.
Thank you. Thank you, Akash. Do you have any questions? Tarian.
Hi, thanks for a really interesting talk. I was wondering if you were able to consider hydrogen bonding in your quantum mechanical simulations of the mixtures, especially when the planets are cooling down. Thanks.
Sorry, so So you are saying that do we consider hydrogen bonding, or like are you saying that do we consider if hydrogens are like hydrogen molecules are bonded or not over time as the planet cools, or did you
Like
mean...
hydrogen bond in between the water molecules as things start to cool down?
Yeah, so in this case, so in this case, we are taking into account like all the interactions that are possible, and are like these. So yeah, so like I think we are like, sorry. So let me take a step back. In a nutshell, we are taking into account whatever the relevant like forces are at the relevant temperatures and pressures. And so yeah, and in these simulations, we only go down to like 750 Kelvin. So yeah, so and down to like 1 gigapascal. So in that pressure temperature regime, we are taking into account all the like relevant forces. So basically, we at every time step we solve the density function theory equations to figure out how exactly these this atomic system is interacting.
Okay, thank you.
Estelle, please.
Yes, hello. Thank you for your talk. I was wondering, in the context of planets that are a little bit colder than Neptune, so like ocean worlds, where you have like a very deep ocean overlaid by a hydrogen atmosphere. Do your quantum calculations allow you to put any insights on how the water propagates from the ocean into the atmosphere, and how much water we can expect in different layers and at different pressures?
So yeah, thanks for that question. So here we are basically looking at conditions in which there is saturation, basically. So in certain cases, there might not be saturation. And so there will be other physics that we'll have to look at. And also, as you were saying, as you pointed out, like, we are not actually looking at really cold temperatures. Because if you're talking about like an icy mantle and how that is interacting with like just hydrogen gas sitting on top of it, that is not something that we are looking at in this at the moment. But definitely would be interesting to see like, in the future what we can see on that front also.
Okay,
and yeah, I don't know if
much.
there might be some experimental data also on that front, but yeah, unfortunately, I'm not very well aware of that.
Thank you.
Antigona, please.
Hi, it was a great talk. Thank you very much. I have two questions. One is about the critical curve, how much it would change if you consider ammonia, because I suppose if it changes it, then the thermal evolution and the interior evolution of the planet would change too. And my second question is while you were talking about this, the mixture of hydrogen and water, I was trying to imagine the formation of the planet itself, because you have all these grains with ices, and at the same time you have the hydrogen from the disk. So how is the differentiation of these icy water planets? I suppose it's different from the ones that for a terrestrial planet, for example. So I don't know if you could share some thoughts about how do you see this differentiation while the planets are forming.
Yeah, thank you for those questions. So first of all, about your first question, that is definitely something that is like on my list of things to do, something I would like to explore more in the coming years. That what is the impact of these other species on the dissolution of these mixing properties? How can that affect what we are seeing in the interiors? And like ammonia is a big major species for these Uranus, Neptune like planets. But yeah, unfortunately, I do not have any any results to show or discuss at this point. But I would love to share about those results whenever I have a better handle on that front. Regarding other questions, that is definitely true. It very much depends on how exactly the planet formation process happens. So if you were to have cold, planet on which you end up accreting some water at a much later time, or some hydrogen atmosphere at a much later time, and it is like completely cold, then of course you cannot expect them to come naturally mix into each other, because their conditions will not be relevant, will not be right. But what you could imagine is that when the planets are like really hot, and it at those like high, and so when temperatures are like really hot, and during those times, if you are accreting not just the hydrogen atmosphere but also these icy pebbles at the same time, then during those formative years for a planet, you might end up getting not a differentiated layer, but rather just a mixture of all these, just because that will be more thermodynamically stable. That being said, we do not actually take into account like large motions in the planet. Like we do not actually consider like big convective cycles, if they can have, and what kind of impact those can have. That being said, again, at high temperatures and pressures, you will expect the system to be substantially convective, and so you would, you would expect a lot of like mixing to be happening because of that. But again, exactly how the formation process happens is something that definitely needs to be like thought about more. So, and yeah, that can be definitely be critical.
And one can test where, please.
Hi, Akash. I have a question about your ab initio molecular dynamics to calculate the phase diagrams. So did you follow a free energy criterion to get the critical curve between miscible and immiscible regions? I wasn't sure. How did you calculate that curve?
Yeah, so we do not use thermodynamic integration. I think that is what you're referring to. So rather, what we basically do is these two-phase simulations. So let me just go back a little bit.
So you kind of quantify the H2O region and H2 regions from your simulations. You don't use any energy criterions to.
Yeah, exactly. We do not use, we actually let these, we have a pure water system and a pure hydrogen system. Basically, we just put them together and try to figure out to what degree they interact or not. This, on the downside, like these simulations end up being much more computationally expensive, but then on the positive side, I feel like they are much more representative of exactly this interaction.
Can you please comment about the accuracy of identifying the miscible region, especially, how difficult it is actually to really see these two phases to be all the time separate in the immiscible region, because you are kind of eyeballing, and even if you use some radial distribution functions or things like that to separate out these phases or to see them together, I'm not sure how easy it is. I use routinely energy criteria to calculate such phase diagrams. That's why I'm curious.
Yeah, so we do not actually. So let me, just a second, let me pull up this plot to show what exactly we're trying to do here. Now, I did not try to go into this in more detail, but what we are basically trying to do is we are trying to pan out this coexistence curve. So basically, this tells you that at any given temperature and pressure, what amount of, like in some hydrogen-rich case, what amount of water there can be. And so, for instance, you can get data points on like at this level that, okay, like you can get that at some temperature pressure, this is how much things can mix. At another place, we can get like a data point here. And that basically helps you pan out how exactly this coexistence curve looks like. And that can then tell you this critical pressure at a given temperature. And this is how we try to, and this like ultimately the critical curve is basically a locus of these critical pressures, which basically is telling us that beyond this pressure, there should be like hydrogen water should be completely miscible. And so this is the approach that we are trying to take here to really figure out what's happening out there. But yes, there will be some error like in these calculations. Yeah. There will be some errors, but yeah, unfortunately, I do not have those like at present to show you. But yes, we are also taking into account that, okay, like given that, but yeah, like more or less, this is how we are approaching
But thank you for answering this question. So how big do you think is that error bar? Like, I mean, is there a few percentage when you go to determine that critical point, like few percentages of pressure or temperature? How big is that error bar?
Yeah, I think it's a few percentage.
Okay. And what potentials do you use? And are you happy with the potentials when you are using them for ab initio MD, especially for oxygen bearing system? Do you see any critical transitions in the phase transitions within a liquid phase like H2O as you keep changing the pressure and temperature?
Yes. So for most of these simulations, I think water is in the critical. We do not really end up going like below like 650 Kelvin or something. We are in the regime where water is more or less like supercritical, or when we end up going to really high pressures, we do see that you end up getting this like ice 10. So when you end up going to like 100 gigapascals, 4000 Kelvin or something like that, we do end up seeing that, okay, you end up getting ice 10. And so, yeah, so we do see that change. And we are basically using the potentials from like the VASP simulations, basically the VASP package, and like we are using the PBE-SOL approximation, basically. PBE-SOL for solving these. So yeah, on that front, yeah, that is how we are approaching this in short.
Thank you.
Yeah, let's move on. We have a question from Eric in the chat. Eric, do you want to ask yourself, or I can read it for you?
Yeah, I can ask it. Thanks. It was a great talk. I was just wondering if they're in the probing the composition of the core and how that affects the radius valley, if there's a degeneracy with the characteristic mass of the core, and if so, how would you break that degeneracy?
So yeah, thank you for that question. So if I understand correctly, so are you asking me that in the context of this radius valley, in the context of this radius valley, you are asking me that how certain we are about the composition of the cores of
yeah, and whether there's a degeneracy with the characteristic core mass.
Yeah, absolutely, there is definitely. So for instance, I was saying that, okay, these are like Earth, these planets have like Earth-like densities. And so what I really mean by that is that, so first of all, when I say Earth-like densities, what I was trying to say was that densities for like a planet, density of a planet, if they were scaled to like an Earth mass. So if you consider the density of a planet when they are scaled to Earth mass, we can say that, okay, these planets that we are looking at should have densities somewhere around like 4.5 to like 5.5 kg per meter cube, more or less. Sorry, grams per centimeter cube, more or less. But but like that is more or less all that we can say. And so what we can say with basically confidence is that these planets do not have, like most of them, like the majority do not have densities of 1.3 or 1.9 grams per centimeter cube, which is more representative of pure ice planets. Neither they are more representative of like iron rich, which will be something like 13 grams per centimeter cube. But we can say with confidence that it should be something around like 5 grams per centimeter cube, plus minus like 0.5 or so. So yeah, so there's definitely a degeneracy, but yeah, so that is a degree to which we can say what the interiors might be, what the bulk densities might be like.
Thank you.
Okay, one last question. I think Estelle, do you have one more question?
Yes, I have one more question. So going back to photo evaporation and core-powered mass loss, is there any study that explores the combination of the two? And do you think that would lead to a better explanation, or do you think they're mutually exclusive?
Sorry, I think there's some background noise. So I did hear the first part of your question. You basically asked me if there's any effort towards combining the both, right? That was your first.
Yes, like are they how mutually exclusive are they? Are they, and would a combination of the two give a better explanation and overlap with the observational surveys?
Yeah, I mean that's an excellent point. Because if you really think about it, like, if you take a step back and really think about what's happening here, what is basically is the case is that we have a planet with an hydrogen atmosphere on the top of it. And what we are basically saying is that, okay, let us provide some energy source to this hydrogen atmosphere. And if that time integrated energy source can overcome the gravitational binding energy of the planet, then you can lose that atmosphere. So in a nutshell, the argument is simply that. And these different methods at the moment are just talking about different ways in which that energy could be coming in, could be getting injected. And so there is no reason to think that why only one could be happening. Ultimately, you definitely expect all these mechanisms to be contributing to some degree. And going forward, like our group and James Owen's group are working towards like developing a more unified model for like a more unified hydrodynamic theory to figure out what's exactly happening out there. So we are definitely working on that front. And so yeah, once we have that, and once we have that model, I think I'll be able to then better comment on what if we can do better job at explaining the observations or not. But yeah, at the moment, what we're basically exploring is that taking them as and member cases, which of these two might be dominating the planned emission or not. But ultimately, yes, we want to combine these and then look at the problem.
Okay, thank you.
And thank you. We already run out of time, so we have to stop here. And let's all thank Akash for the awesome talk again.
Thank you. Thank you so much for having me again.